Okay, today we are going to be talking about Newton's laws of motion and periodization. So we're going to be the first thing we're going to do, give an overview of Newton's three laws of motion, and then after that we will get into a brief discussion of periodization and also from periodization an application of Newton's laws of motion to strength and conditioning. Newton's three laws of motion. Sir Isaac Newton has when he was doing his thing back in the day, he came up with three irrefutable scientific laws. First one is the law of inertia. The second one is summarized in the equation force equals mass times acceleration. And the third one is the law of action and reaction. These govern all bodies in the world, in life, but in terms of this discussion, they're going to govern all of the bodies in the weight room. That's specifically us and the weights in the weight room. So the first one is that law of inertia. The law of inertia states a body in motion stays in motion and a body at rest stays at rest unless acted on by an external force. In other words, in the weight room, the weights are going to be at rest. And then in order to get the weights in motion, we have to apply an external force coming from our muscles and using that, the movement cascade that we've talked about. So with our movement cascade, we're looking at bones, muscles, joints, ligaments, and tendons. And remember, the bones are the levers. The force, we'll be getting into force in a minute, but the force is coming from the muscles, and the joints act as the axis of rotation in that lever system. The ligaments join bone to bone, essentially creating the axis, creating that joint. And then the tendons are what links muscle to bone. So my tendons are essential for transmitting the force that's created by the muscle into the bone, where the bone acts as a lever to magnify the force. And then the bones rotate around the joints, and we have human movement. So with our law of inertia, a body in motion stays in motion, a body at rest stays at rest, unless acted on by an external force. When we look at this lever system of the body and we think about the body in an anatomical position, the body will stay in that anatomical position, which is at rest, unless it's acted on by an external force. The muscles will create force by shortening, and the muscles will pull on the tendons. The tendons pull on the tendons pull on the bones, and then the bones rotate around the joints, and then we have our human movement. So that's our law, the law of inertia. Body in motion stays in motion, body at rest stays at rest, unless acted on by that external force. We think about this also for my athletes when they're going for a 1 rep max, a 1 repetition maximum. That's going to be a very slow motion. It's going to be a very high force motion. We're going to be overcoming a lot of resistance. In the squat, it takes about 3 seconds for the body to go from the bottom of the squat to the top of the squat from a globally flexed position inferior to the transverse plane to a globally extended position inferior to the transverse plane during that maximal squat. So that's our law of inertia. Body in motion stays in motion, body at rest stays at rest, unless acted on by that external force. The next one that we take a look at is the equation force equals mass times acceleration. So when we take a look at, if we break this down, looking at it from from a strength and conditioning perspective, mass tells the sports scientist how much do I have, or answers the question, how much do I have? If we look at say a 20-pound set of dumbbells, I got 20 pounds in each hand, the mass is going to be 20 pounds. Or if we're looking at humans, if I have a distance runner that weighs 140 and I have a shot putter that weighs 250, well, the shot putter has almost twice the mass. With a shot putter, I almost have twice as much human as I do that distance runner. Now let's take a look at acceleration. So with acceleration, there's a couple of things to keep in mind. Acceleration is going to be a change in velocity. And when we take a look at velocity, velocity gives me speed and direction. So speed, how fast I'm going, and direction is going to be which way am I traveling. And velocity is a vector quantity. Because it has both magnitude and direction. So magnitude tells me how much, direction tells me which way. When we're looking at velocity, when we're looking at acceleration, if I have a body, and let's just say I have an athlete, running, and we'll just put them right here. You will use we'll just use a box. That's the beautiful thing about physics, is that you can just draw a box and call it what you want. So that's our, I don't know, we call this a softball player running down the first base line, and they're running this way. So this is going to be a force. We have a certain amount of mass here, and then we have a certain amount of direction going this way. So this vector is going to be our force vector. Let's clear this off. Now, the next one that we take a look at is our law of action and reaction. For every action, there's an equal and opposite reaction. So in other words, if we were to look at a push-up, with a push-up, when we push into the ground also pushes back on us. Or when we take a look at a sprinter, with a sprinter, when their foot hits the ground, this is my sprinter's foot here, and they're going to hit the ground, they're going to drive a force into the ground, and then the ground is also going to exert a force back up. So the law of action and reaction is critical when we're looking at human performance, because the more force I can put into the ground, the more force the ground gives back to me for a sprinter as I move down that track. The sprinters our elite sprinters have enormous feet not only in terms of size, but also in terms of musculature. And the foot, that large muscular foot, is what allows that athlete to put so much force into the ground. And the more force they put in, the more force it's going to come back. So when we start looking at strength and conditioning, we'll clear all these out, clear out our drawings. Our law of inertia, a body in motion stays in motion, a body at rest stays at rest unless acted on by an external force. If I'm a hockey strength and conditioning coach, this law right here, this law of inertia, is going to govern my strength and conditioning program, because hockey is a collision sport. And the more force, the more external force my athletes can generate and exert on the opposition, the better my team is going to do. When we take a look at hockey, basically, you can summarize hockey as a race and a fight. It's either a race to the puck and then a fight for the puck, or a race to an empty space on the ice and then a fight for that position on that empty space. So if my team is bigger, faster, stronger, they're going to be able to exert their will, exert their force on the other team. The next one, now we pair this up with, how do we get more force? Right here, mass times acceleration. When we're looking at force, we can do one of two things. We can either move to increase force, we can either move more mass at the same acceleration, that'll give us more force here, or we can take the same amount of mass that we're using and move it faster. Those are our two ways to increase force. And then over here, for our law 3, for every action, there's an equal and opposite reaction. Again, we'll look at hockey players. We'll look at playing defense. If my Ds if we know that for every action there's an equal and opposite reaction, and we know that for every a body in motion stays in motion, a body at rest stays at rest. So if my athletes are able to deliver high force to the opposition, we're going to be able to knock them off the puck, and we're going to be able to win puck battles. So these are our 3 laws. Quick overview as to how to apply them. We'll clear out our drawings. Taking a look at our next slide. So the math of force, work, and power. I'm not going to put numbers in here, but what I am going to do is explain these so that when we move into applying this to strength and conditioning, we'll have a working knowledge of what force, what work, and what power is. So we said a minute ago, force is mass times acceleration. Mass, how much stuff do I have? How much of a hockey player do I have? How much of an offensive lineman do I have? Acceleration. Basically, we can look at this as how fast is it moving? And with acceleration, this gives us that vector quantity. This gives us that magnitude, how much, and direction, which way. In terms of math, force is calculated right here. Our slide got away from us. Force is calculated right here. Change colors, go with the red. By multiplying mass times acceleration. So force is the product of mass times acceleration. In the weight room, we can think about force as our 1 rep max. So how much that classic, how much do you bench? So what's our bench max? What's our squat max? What would our hang clean max be? But here, when we look at force, this is going to be the body's ability to move large amounts of resistance through a full range of motion. And that's the first one in our trio of our formulas here. The next one we take a look at is work. Work is force times distance. Work tells me my capacity. An example of work is going to be our Fitbits. So if anybody has a Fitbit or if anybody has an Apple Watch and you look at steps per day, that is going to be a measure of work. Work is, when we break this down in terms of steps per day and looking at it in terms of a Fitbit, the force right here is going to be your body weight. So with, we'll look here at steps per day. Steps per day is a measure of work. So what we can do here with physics, one of the identities is that force, when we look at force, it can also be mass times gravity, because gravity is a form of acceleration. Gravity is the downward vector. It's going straight back into the earth, and that pulls us down at 9.8 meters per second, meters per second squared. And then in terms of like when I was teaching AP physics, we would round this up to 10 meters per second squared. So this is acceleration due to gravity. So when we're looking at steps as a measure of work, well, we have force as equals mass times gravity here, and gravity is what we're overcoming as we walk. And then the other thing that we look at is our distance. So now in here, we have force equals mass times gravity. And then when we look at our daily work, it would just be force times steps. And then if we wanted to get really technical about it, we would say steps times 1 meter. Yeah, steps times 1 meter. Because the typical human stride is about 1 meter, about 1 yard, 3 feet. So this is how we could, if we were a personal trainer, we could use steps as a measure of work. The science behind it. If I were to get back into the personal training biz, I would just look at steps. I'd say, all right, you need to hit 10,000 steps today, and that's going to be an example of work. It doesn't tell me how I got my steps. It just tells me that I got my steps. And when we look at athlete monitoring, that's going to be the first step. If I can just get 10,000 steps, I don't care how you do it today, just get 10,000. In terms of our equations, work equals, so we drop the F in here. So work is force times distance. Force is mass times acceleration. So work can be mathematically represented as mass times acceleration times distance. It can also be represented mathematically as force times distance. What's going on here with work, again, is my body is generating a given amount of force, and I'm going for a certain amount of time. Another example of this, think about pushing a sled. So for my football players, if we have a field here, we have 100 yards, you have a 100-yard field, and we're going to load up a sled. So let's just say it's a 100-pound sled. And we're going to take that sled and we're going to push it 100 yards. We have 100 yards, and our sled equals 100 pounds. So now we can come up with a value for work. The next one we take a look at is power. Now notice, here at work doesn't give a rip how long it takes you to get this sled from point A from point A to point B. It could take you a minute, it could take you 10 minutes, or it could take you an hour. If you go from A to B, if you push that sled from A to B, 100 yards, 100 pounds, everybody will do the same amount of work. Athlete 1, it takes them a minute. Athlete 2 takes 2. Athlete 3 takes 10. They all do the same amount of work. But we look at power. Power is the ability to do work quickly. Power is going to involve time. So let's put our 3 athletes up here. We got athlete 1, and let's just say it takes athlete 1, I don't know, 45 seconds to do this push. Athlete 2, it's going to take them 60 seconds to do that push. And then athlete 3, well, they're on the struggle bus, and it takes them 120 seconds to do that push. So here, athlete 1 generated the most power because they had the shortest time. Athlete 3 generated the least power because they had the most time. That denominator is going to be high. Remember, go back to math. The lower the denominator here, the higher my quotient is going to be over here. So looking at power, power is force times velocity. Power is the ability to do work quickly. That was how power was described to me back at the Cuse all those years ago. So when we're looking at developing power, we're looking at the ability to do work quickly. And then here we have this work over time. So when we want to improve power, we can do it one of 2 ways. We can improve work. We can increase our work capacity and do it at the same amount of time, or we can keep our work capacity constant and do it quicker. Another way to look at power is going to be force times velocity. And we arrive at this one because we have power equals, and then here with work is mass, or all right, so we have force times distance here divided by time. And then if you remember from math all those years ago, where we have velocity equals distance divided by time. So now we can take our force right here and our velocity from here, and then we end up with this identity of power is force times velocity. And I like this one because when we're looking at it from strength and conditioning, and we're gonna move into that in just a second. We're gonna get away from this science. But here, as a strength coach, well, I can increase, if I want to improve power, the first thing I'm going to do is I'm going to increase my ability to generate force. And then the second thing I'm going to improve is my ability to move quickly. So this will be our prioritization for our strength and conditioning framework. And we'll clear all this out. All right, taking a look at periodization. So we've talked about force, work, power. Now we want to look at how are we going to use this? It's all well and good in theory, But in strength and conditioning, how do we use force, work, and power to guide our training program? We use what's called the periodization framework. Periodization is a training theory that was created in an attempt to recreate athletic success. In other words, we want to try to create a cookbook or a set of directions or a flow chart so that our athletes will arrive at their peak when it's most important, namely at the end of the season. So periodization, training framework based on training cycles. We have our macro cycle, which is going to be our training year. We have our mesocycle. Mesocycles are approximately 4-week blocks that have an overarching goal. And then we have our microcycles. These are 10 to 14 day specific plans where each day contains my daily training. So with our macro cycle, and I'll use the example of lacrosse. I learned my periodization framework at Syracuse back in the day when we were going to the Final Four in lacrosse every single year. And we would use one of the things that we would do is use our major holidays as milestones in our periodization framework. So our training year would go from the day after Memorial Day to Memorial Day every year, because Memorial Day was the day that the NCAA lacrosse final, the championship final game was played. And so we're training for that game. And then we would have, with our mesocycles, we're going to have our overarching goals. These are going to last approximately 4 weeks. And then from a strength and conditioning perspective, we'd have our microcycles right around 10 to 14 days. And as the season goes along, this is where we're programming around games, we're programming around rest periods to get our athletes to play their best on game day, but also for them to play their best in May. In the college lacrosse world, we talked about our 2 key months, March and May. March is where you have all of your major non-conference games. So when we were playing Johns Hopkins and Hopkins Syracuse is just a huge rivalry. We play them in March, and that would be a must-win for us. So we taper down a little bit. But then coming into May, in May it's one and done. You lose, you're out. Next day you're counting lacrosse balls. We had to have the boys ready. So let's look at what we're going to do is look at 3 mesocycles. I lump them together and I call them GPP, general physical preparation. So here with our GPP cycle, like I talked about with at the Cuse, this is how we would do it, is that the GPP would run from July. It would be July, August, and September. And then so here, so we would play until May, and then we'd give them the month of June would be our active rest period, where I want you to stay healthy, I want you to stay active, but I want you also to rest and recuperate from the previous season, because in July we're going to get going. Now you can see here we have a 3-month cycle. We have, so with our GPP is going to be 3 mesocycles. And in July, our goal is going to be to increase our force production. In August, our goal is going to be increase work capacity. And then in September, we are going to devote that to power and also speed. Power and speed in September. So here with our 3 mesocycles, for the first month, our overall performance objective is going to be to get the athlete strong. We want to bring up their 1 RM, their 1 rep max. So our A priority is going to be in the gym, lifting heavy, 5 sets of 5 reps. That's my go-to for force development. And then in August, we are going to transition. Now we've got them strong. So now we go into our work capacity. So we're going to develop endurance. So here we would use something like a complex where you would do some sort of a high force. Let's look at a bench press. So maybe we do a bench. We'll do a bench press for 5 reps. And then from the bench, we may move into we may be just doing this just along a bodybuilding framework. Maybe we move into a push-up. We do a push-up, and we're going to do this for, say, 10 reps. And then PUSH push-up. And then from there, we may move straight into if we have a facility where we can do this, we may move into like a 40-yard stride, 40-yard strider, and we'll go over here, and we may do something like 5 rounds of this. So here, to develop this work capacity, we'd go bench, right into push-up, and then get up off the push-up, and then right into a 40-yard strider on the turf in the weight room. If I have a weight room that has a 40-yard strip right down the middle, or maybe we go outside in the parking lot, we do it there, and then we take a little bit of a rest, we let our body recover, and then we come right back to this. So this is going to be a little bit different than over here if we're doing 5 by 5 bench with say on a 2-minute clock. Because what's going on here, every 2 minutes we lift. Over here, we do 5 rounds of bench, or 5 reps of bench, 10 reps of push-ups, 40-yard strider. And then now over here in our power mesocycle, now we move into the ability to move weight fast. So maybe here, our A priority is going to be something like a medicine ball chest pass. So now what did I do? I got my athlete strong for a month. I devoted that to getting them strong. Then for the next month, I devoted them. We're going to take this strength and we're going to improve, and we're going to take it and increase their endurance. And then once their endurance is built, now we get them moving fast. When we're done with this, we move into fall ball. And fall ball is going to be our where strength and conditioning doesn't become our A priority. Strength and conditioning becomes our B priority. We put strength and conditioning on a maintenance, and now we're teaching and training for sport, for, in this instance, the sport of lacrosse, culminating with a fall ball tournament. And so this is how we use Newton's 3 laws of motion to govern strength and conditioning. And we'll shut this down, and how we use it to set up our general physical preparation cycle.